Welcome to my talk on non-line of sight reconstruction using efficient transient rendering. I am Matthias Hullin from the University of Bonn. The topic is non-line of sight sensing, or the challenge of seeing things that are around a corner and obscured from our direct view. You may have heard about a man by the name of Johannes Gutenberg. Around the 1430s, they were planning a major religious event in Aachen. The problem at the time was that if you're a pilgrim in a crowd, it's really hard to catch the magic radiation that's emanating from the relics that are on display. So Gutenberg invented a device with some holy mirrors inside, sort of a periscope to extend the direct line of sight. His plan was to make a batch of these devices and sell them to pilgrims so they could see over the heads of the people in front of them in the crowd. That religious event, by the way, never happened. It was cancelled in order to prevent the spread of an infectious disease. Meanwhile, imaging technology has come a long way. Today we have not only cell phone cameras but also self-driving cars with all sorts of sensors and medical endoscopes the size and shape of a spaghetti that image the insides of our bodies. However, the fundamental challenge remains. If there's something between us and the thing we want to see, we can't see it. Despite all the sensor data, there might be a bike coming out of a narrow side street that we can't sense until it's too late. And the thing that's causing our belly pain might be one bend further than what the doctor can reach with her endoscope. So there's a long history of people trying to extend their line of sight and many important applications that could benefit from it. Computational imaging techniques could bring an important breakthrough. In 2012, Andreas Felten and co-authors proposed a setup which is now considered to be canonical for the non-line of sight sensing problem. Imagine we have an unknown object that we can't directly observe because it is occluded from our view. However, there's a wall nearby that we can see. So we can take a laser and illuminate, say, a point on the wall, and part of the light will scatter to the object, and part of that light will reflect from the object back to the wall. This reflected light we can then pick up with a suitable sensor. So, like Gutenberg's periscope, we're using an intermediate surface to indirectly image the object. However, the periscope uses a mirror. Among the properties of a mirror is that if you send one ray of light in, one ray of light comes out. Directional information is preserved. Our wall, in general, is not a mirror. Any ray of light that it receives will be scattered in all possible directions. So we lose the directional information that we would have with a mirror. However, using today's equipment, we can use an additional dimension of light transport, the time of flight. Even for diffuse surfaces, light that gets there first gets reflected first. So if a surface is illuminated by light with a certain temporal distribution, that distribution does not change upon reflection. If we now illuminate a point on our wall with an ultra-short laser pulse, we get a wavefront that interacts with the hidden scene and after returning to the wall gives us rich patterns of light that encode information about the scene. Such light patterns can be measured using suitable devices like streak cameras or ultra-fast photodiodes. We call them light echoes, or more technically, space-time impulse responses. How do we get information about our hidden scene from a space-time response? Different approaches have been proposed over the last decades. Among the first observations made by researchers was that each intensity value measured in this setting integrates contributions with a fixed time of flight, which corresponds to an ellipsoidal shell. The adjoint operator is ellipsoidal back projection, where any portion of detected light is basically smeared out over all locations in space where it could possibly have been reflected. Then came linear inverse formulations, inverse filtering approaches both in space-time and Fourier domains, nonlinear refinements to all these methods to include occlusion and BRDFs, wave field propagation methods similar to Rayleigh-Sommerfeld diffraction integrals, very clever exploitations of the Fermat principle and other approaches where isolated events on the time axis serve as the main source of information. More recently, we've started seeing the first machine learning approaches for distinguishing between a small number of objects in different positions. When we reconstruct something we can't directly see, it is of course important to have a way of verifying our reconstruction. So how correct is our reconstructed model? Well, we can't tell, as there are always ambiguities. The side of the object that is facing away from the wall, for instance, does not show up in the data at all. But if we have a reconstruction and we render it back using a physically based image formation model, the result should be consistent with the experimental observation. Or, put the other way around, if the predicted response agrees with the actual observed one, then we can tell that our solution is a good one, at least under the model assumptions that we used. Having an non-line of sight renderer at hand enables novel approaches to the reconstruction problem. Given the real-world scene and measurement setup, one way of addressing the reconstruction problem is to construct a virtual version of the measurement alongside the real one. If we have a hypothesis of our scene, we can predict the response we should get from the experiment. And then we wrap an optimization loop around it that aims to minimize the difference between prediction and observation by refining the scene hypothesis. That is the approach we follow in this work. Before we talk about implementation details, let's look at the set of features that makes the renderer suitable for this sort of analysis by synthesis approach. First of all, we need the renderer to simulate above everything else light that has been reflected 3 times, on the wall, on the object, and back on the wall. We need our renderer to produce results that, even if not 100% physically accurate, are quantifiably close to it. The residual from a perfect reconstruction should be close to 0. We need our renderer to be extremely efficient, since over the course of the optimization run we keep rendering over and over again. In total, we might need to produce hundreds of thousands of predictions or more for a single reconstruction. Of course, our input data is noisy, but our simulator must avoid stochastic noise at all costs, because it would be absolutely toxic for computing numerical derivatives. And then there are a few more features that are nice to have, and others that we don't need at all. Note that among these is direct illumination. So our renderer does not have to be a good renderer in the traditional sense. In principle, path tracing is general enough to accommodate this setting. Its main problem is the significant amount of Monte Carlo noise that it produces. The rendering shown here at a resolution as low as 16 by 16 pixels took hours of runtime and hundreds of millions of samples and still has noticeable noise. Perhaps this could be improved by importance sampling the contributions of the hidden scene. We are not aware of any practical way to importance sample indirect reflections by scene geometry, so for now there's not much we can do. In contrast, we've designed a renderer that, at least when judged by traditional criteria, is actually quite bad. It can't even do direct illumination. However, it can do the reflection order that is relevant for non-line of sight scenarios, namely light that has bounced exactly 3 times. And that it can do extremely efficiently, delivering nearly physically accurate and noise-free predictions in a matter of milliseconds. So it checks all the boxes for non-line of sight rendering, and it does so at the expense of generality. I should also mention that a lot of non-line of sight methods rely on a volumetric image formation model, where the scene is represented as a cloud of scattering densities. This representation choice enables the use of linear light transport operators, but it makes it hard to represent opaque surfaces that have an orientation and shadow other parts of the object. So how do we render around a corner in a way that is both close to physics and really fast? In a non-line of sight imaging setup, both light source and camera are collimated. That is, they emit or receive light basically along a single ray. By pointing either device at the wall, we can generate a virtual omnidirectional emitter or a virtual omnidirectional detector. The first and last segment of the optical path do not depend on the scene, so we can leave them out of the simulation and only look at light transport from the laser spot on the wall to the object and back to the observed position on the wall. This gives us an unwarped transient image whose coordinate system lives on the wall. The time of flight in this representation is simply the combined length of the segments A and B divided by the speed of light. Let's have a closer look at the radiative transport for this special type of optical path. We need to compute the integral of all light coming from the laser spot WL that gets reflected into the direction of the virtual detector WC over the whole scene, which in this case is the object O. F is the BRDF. Eta is the geometric coupling term that combines the visibility function V and the light attenuation from Lambertian cosine terms as well as inverse squared distances. We have one such term for each of the 2 segments of the optical path. Note that by neglecting interreflections, we do not ever have to integrate over area light sources. Every point on the object receives light from the laser spot if it is visible and from nowhere else. So evaluating this integral is a lot more efficient than it would be to solve the standard recursive rendering equation. This property is retained across all captured geometries that are commonly used in non-line of sight reconstruction, including O'Toole's coaxial geometry, setups with one laser position and many receivers, as well as setups with a scanned laser and a single detector. The key to making the evaluation of our integral really fast is to directly work on the representation of our object, which is given as a triangle mesh. For sufficiently high resolution, it is safe to assume constant radiance over each triangle surface and only take the centroid ST into account. The integral thus becomes a sum where each triangle contributes with a weight that is its area. Each visibility test is performed only once per triangle, namely for the rays connecting the triangle centroid to the emitter and detector locations on the wall. We implemented this test using optics on the GPU. To obtain a time-resolved rendering, the light contributed by each triangle has to be accumulated in a time-of-flight histogram. Each bin corresponds to a certain interval of optical path length, from emitter to a point on the object and then to the receiver. If we represent each triangle only by its centroid, all of the triangle's contribution will fall into a single time bin. In general, however, larger triangles should have a temporal support that spans multiple bins. For instance, here we see that the 3 corner vertices of the triangle end up in different time bins than the centroid. Ignoring this leads to the artifacts of the kind seen here for a 4x4 square grid. The coarser the discretization of our object, the more severe the artifacts. Note that this rendering here already features a filter that linearly spreads each contribution between two adjacent time bins. Without this basic filter, if a triangle centroid moves from one bin to the next, its entire contribution would pop at once. The resulting output would be discontinuous and impossible for most optimizers to deal with. But even with linear filtering, the output is not smooth as it should be for a continuous object surface. What we get is the response of a set of isolated points, and it does not reflect the triangle's actual spatial extent. We can reduce these spatiotemporal aliasing artifacts by refining our triangle mesh to a resolution that is sufficiently high to reduce each triangle's temporal footprint. On the other hand, this also raises the rendering time significantly. To enable smooth rendering even at very low mesh resolutions, we employ a new linear temporal filter that distributes the triangle's light contribution over its entire temporal support. We interpret the irradiance value computed for the centroid using the terms seen before as the area of a tent that extends between the arrival times for the three corner vertices of our triangle. The irradiance portions assigned to each bin correspond to simple trapezoidal areas that are easy to compute and depend on the triangle geometry in a continuous manner. Using this filter, we are able to generate smooth renderings even at very coarse resolutions with a minimal impact on runtime. Let's compare the output of our renderer to a path-traced ground truth. As gold standard, we used Jarabo's renderer, which is based on PBRT. In this representation, the x-axis are the pixels and the time bins are shown on the y-axis. Without temporal filtering and proper visibility tests, our results are significantly different from the ground truth result. In particular, some surfaces contribute to the rendering even though they should be occluded by other parts of the object. We also see that the coarse discretization of our geometry leads to severe differences to the path-traced ground truth. By combining our visibility test based on ray tracing with our new temporal filtering, we are able to generate renderings that come very close to the ground truth. There are no more false positives. Together with the absence of discretization artifacts, this brings us up to 0.5% to the Monte Carlo path tracer. That's okay, but of course it would be nice to go even lower than that. So where's the remaining 0.5% coming from? Here, we see the error between our rendering and the path tracer as a function of Monte Carlo samples per pixel. As we can see here, it's the path tracer that is not fully converged. So let's not worry about lack of accuracy in our special purpose renderer and instead enjoy just how fast it is. 16 by 16 pixels, hours of rendering time using a path tracer, 40 milliseconds of render time using our renderer. We can also render the same scene at a lot higher spatial and temporal resolution and still be done in less time than it takes us to appreciate the result. This brings us to the actual non-line of sight reconstruction, which we achieve by wrapping an optimizer around this efficient and nearly physically accurate renderer. On one side, we have the real experiment, real capture devices, and real input data. On the other side, we have a virtual version of the experiment. The scene is generated by some function g that takes a parameter vector p as argument. Piping its output through the renderer produces a prediction of what we should expect to observe under the given scene hypothesis. The goal then is to refine the parameters so that the prediction and observation become as similar as possible. How do we represent our scene? Our goal here is to find a parameterization that is low-dimensional and also produces well-behaved gradients when fed into the forward model. Inspired by ideas from point cloud reconstruction, we modeled the scene as the level set of an implicit function. Our parameter vector p describes a list of Gaussian blobs. Through most of our experiments, we used isotropic Gaussians, but other functions work as well. This way, we are able to reduce the number of unknowns from thousands or millions for a full mesh or volume to 4 variables per blob. We need 3 unknowns for the position and 1 for the variance. From this sum of Gaussians, we generate a triangle mesh using the marching cubes algorithm. Let's get to the optimization. I won't go into the details here, but only mention some key points. We first randomly sample a position in the reconstruction volume. We then jointly optimize over a manageable number of blobs that fall into this neighborhood, namely 10. This keeps the number of variables low, while allowing the optimizer to recover complex geometric features that are influenced by more than a single blob. Blobs that are initially placed in wrong positions almost always raise the cost. To avoid degenerate solutions, we optimize in 2 passes. First, we optimize only the blob positions, then positions and size. Also, we are using numerical differentiation because it's hard to auto-diff visibility. This means that we looked at a lot of blobs slowly wobbling into their right positions. The auto-optimization loop relies on multiple heuristics to reach the global minimum. In short, in each auto-iteration, we mutate the current solution by adding blobs, removing blobs, or by refining the current set of blobs. In a final regularization step, blobs that don't improve the cost by more than a given amount are pruned out. Here we see the algorithm at work, reconstructing a synthetic scene. This is the Stanford bunny rendered at 16 by 16 pixel sensor resolution with 4 different laser positions. as the reconstructed object grows, we can see that the residual between measurement and prediction gets lower and lower. Here's another synthetic scene with a mannequin and just a single laser position. For comparison, we see the same scene reconstructed with the back projection method. Note that our reconstruction is a lot more complete. This is due to the fact that back projection cannot take into account effects like occlusion or surface orientation that are naturally handled by our method. Let's have a closer look at what we want in a reconstruction. On this synthetic scene, we have ground truth, which we can use to quantify how well we are doing. So we want to obtain geometry where there really is geometry. Both missing parts and false positives are unwanted. At the same time, such geometry that we do reconstruct should be as close as possible to the true surface. We measure the deviation using the distance in z direction. In this visualization, a perfectly reconstructed scene should be shown in solid blue with no red or yellow spots. So we want a high coverage of the object and at the same time a low error in the surface geometry. Back projection, like many reconstruction schemes that have been developed since, is based on a volumetric representation, so the object geometry needs to be extracted as an isosurface using a post-processing step like marching cubes. This involves the setting of an ISO value. If the value is chosen too high, a lot of object surface is missing because it does not meet the required threshold. Lowering the threshold yields a model that is more complete, but at the same time false positives are coming up and the error of the true positives increases. There is no ISO value that would produce a reconstruction that is at the same time complete and accurate. Here, our method shows the advantage of working directly on a surface representation. In combination with the constant validation by a physically based rendering step, this leads to reconstructions that are complete and low in error, without the need to choose an arbitrary parameter like this ISO value during geometry extraction. Our method also handles very low input resolutions much better than any known method. This is important because high resolution is equivalent to long capture time. We were able to generate recognizable reconstructions down to extremely low resolutions of 4x4 pixels or only 8 time bins. On the other hand, voting schemes like back projection fail to reconstruct surfaces when they are not supported by sufficiently many votes. The previous results were generated using synthetic ground truth data. At the time we wrote this paper 2.5 years ago, we also tested our method on the only real-world dataset available, which was captured with a single photon avalanche photodiode, or SPAD. We found that our result carves out the shape more accurately than back projection. Note that the SPAD sensor response is not part of our forward model, which only approximates physical light transport up to a very high accuracy, but not much more than that. Since then, more datasets have come out. Quite a few of them have objects with non-trivial reflectance distributions. The S, captured by O'Toole et al., is even made of a retroreflective material. Although we assume a Lambertian BRDF in our forward model, the reconstruction is recognizable nonetheless. Before we show more experimental results, let's briefly discuss what we have. We've got an extremely efficient renderer for space-time responses that only takes a few milliseconds to get really close to a path tracer. Using our renderer as a forward model, we reconstruct scenes around a corner by minimizing the difference between observed and predicted response. The results are good, but the method is excruciatingly slow. This mannequin, for instance, took 24 hours to reconstruct on a not too shabby GPU. This is because for a reconstruction, we need to render not just one, but hundreds of thousands of predictions. It is only thanks to our renderer being so efficient that the reconstruction can finish at all in a finite amount of time. What happens when our model does not fit the real data? When there is background in the signal, spatially varying materials, or sensor noise? Well, it's not impossible, but not easy either. Finally, it would certainly have been nice to do a few more runs on experimental input. So, I'd like to take the opportunity to plug a more recent paper that is based on the exact same renderer but uses it in a drastically different way. Of course, as you would have guessed, the key is to train a feed-forward network to make the predictions in a non-iterative way, which no longer takes days but is really blazing fast. This time, we opt for a depth map representation, as it nicely maps to convolutional network architectures. We generate lots of depth maps following different strategies and predict the space-time response using our renderer. The data is augmented with a simplistic sensor model to make the network robust to dark counts and shot noise. So let's look at how well the system does on a couple of datasets that have been released more recently. These here were taken by Lindell and O'Toole in the coaxial setting, and they include objects of different BRDF and mixed scenes. Although our system is only trained on diffuse models, it nevertheless does quite well on many of these datasets. At least the rough shapes are clearly visible. It takes us 23 milliseconds for the whole reconstruction. We are not aware of any other non-line-of-sight reconstruction method that is faster than that. So, in addition to using our super fast renderer to implement the world's slowest non-line-of-sight reconstruction method, we also used it to train the fastest non-line-of-sight reconstruction method based on deep learning, and successfully tested that on a lot more experimental data. Thank you.